The last two transformations are especially important once we start looking at hardware, right. One of them is called unrolling. The basic idea behind unrolling is very simple. What it's saying over here is there is a significant loop overhead associated with this loop. Can I amortize that overhead? Can I split it across multiple computations? Okay. So what happens over here is I have basically split it across 5 addition operations. Okay. Again, keep in mind this is a trivial example that I am using just to illustrate the idea, but the core concept remains the same. We have a certain overhead associated with the loop. I would like to split that out, amortize that effect. Okay. So what happens over here is now the overhead, the unrolling step itself is done by modifying the loop. The way the induction variable is set up, how it is incremented, and what the comparison is being done. Okay. Now you will probably notice that I tried unrolling by a factor of 5, okay, it worked. What if I wanted to unroll by a factor of 6? Why is that complicated? Because I need to do it 100 times. Okay. But if I do unroll 6 and I change this over here, what will happen is it will go up to 96, and those last 4, 97, 98, 99, or rather 96, 97, 98, 99 will not get executed. It will not add that many times. Okay. If I need to do that, I will need something called the epilogue, right, which basically says 100 modulo 6 is equal to 4, sum plus equal to 10, 4 times. Whatever is that remainder, the last part of the loop needs to actually be done separately. Okay. So unrolling can be done on almost any loop. I mean, in principle you can unroll, you can take any for loop that you have and unroll it. What does it mean? It just means that instead of writing for I is equal to 0 to 100, you write the same code 100 times. So fundamentally there is absolutely nothing preventing that from happening. Will you get benefit from it? That is not very obvious. You may or you may not. Okay. But if you are unrolling by a partial factor, if you are doing complete unrolling, that is you just take that and write it out 100 times, that is easy to do. But if you are doing partial unrolling, it turns out that 5 is perfectly okay for this particular loop, 6 is not. 6 you have to handle with care. You first change the loop in order to do the groups of 6, and then you have to take care of that remainder at the end separately. So you have to have an epilogue. Okay. Now I showed you the case where this unrolling is used for sort of reducing the overhead of the loop, but it turns out that exactly the same thing in the context of hardware can be used for parallelism, right? Because what I can do is I can effectively say, now I have these unrolled by 5 different things that need to be done. Can I do those in parallel? Now the way that I have written the code, what I am doing is I am adding the same value to, or rather I am adding something to the same variable. So this effectively becomes a dependency, right? The fact that I am updating the value of sum. But let us say that I had something slightly different, which basically said for a of I is equal to some function of b of I. Okay. And I rewrote this to look like for a of I equals some function of b of I, and a of I plus 1 equals function of b of I plus 1, right, and I do I is equal to I plus 2 in the loop, right. This is perfectly valid. Now in principle these two could run in parallel, and I can create 2 separate pieces of hardware that do those things in parallel. So unrolling, in other words, is a very simple way of getting parallelism into your program implementation, right. The trivial way of course is complete unrolling. Partial unrolling with a given factor can also be done, so that you have control about how much hardware it uses. Because for example, if your loop is running 100 times, you do not always want to unroll it by a factor of 100. So if you can choose how much the unrolling is going to be done, that is better. Okay. So yeah, the unrolling for parallelism can be done in exactly the same way. You can do this, right? If I had a loop that was doing this, I could have split it out into 2 loops, or rather the same loop but 2 separate steps, in which case A of I update and A of I plus 1 update can be done in parallel. The last topic is something called software pipelining. I may not be able to complete all of this today. We will be finishing this tomorrow and then looking at Vivado HLS for the FFT as well as one more example in tomorrow's class. Okay. The idea behind software pipelining is sort of extending the, it's basically saying, what if I had a set of instructions that could potentially be run one after the other, but I have certain kinds of constraints on them, the way that they stand, right? Let's take a quick look at this. I am assuming that I have a for loop out here with A, B, C, D, E, F as separate function calls, each of which has a latency as specified over here, right? Some number of cycles. This is completely fictitious, but this is an example from Wikipedia, but it illustrates the example quite well, illustrates the concept quite well. What is important is that I have a set of dependencies. In other words, I am going to assume that I need to do things in this order. Only after A of I has completed, I can do B of I, then I can do C of I, etc. Okay, so this order is important. What that effectively means is that my data flow graph for this system looks something like this: A, B, right? There are 6 operations that need to go in order. Now the normal schedule, right, the basic schedule that you can come up with would basically say this takes 3 cycles, this takes 3, this takes 12, again 3, 3 and 3. If I schedule all of this out, what would I get the latency to be? 3 plus 3 plus 12 plus 3 plus 3 plus 3, that is 27 cycles. What about the initiation interval? Once again 27 cycles, because I have to finish all of them before I can go on to the next one. Okay. So now the idea of software pipelining, which is also called task level pipelining, and in the context of HLS will actually be known as data flow pipelining, right, actually says that if I had separate pieces of hardware for A, B, C, etc., how would I go about doing this? How can I actually implement this? But let me consider another example to show that this can actually be applicable even in the context of software itself, and is in fact used like this in many kinds of processors. For example, the TI DSPs, right? They can actually make use of this kind of software pipelining. What is happening over here is, what we are saying is, once A1 executes, next 2 clock cycles are idle, then B1 executes, then 2 clock cycles are idle, C1 executes, 11 cycles are idle. Not idle meaning that no other function or no other instruction can start there, then D1, E1 and F1. This is the exact operation that is happening. Okay. Question is, can something execute here or in any of these gaps? Okay. And what we are going to say is, okay, clearly A2 can. From a dependency point of view, it is possible for A2 to start in the next clock cycle, right? It is not waiting for anything. And we are going to assume that the processor is such that it is also a pipeline processor. It can potentially start this in the next stage, right? So what is actually happening over here? Effectively what we are saying is, the scenario that I am constructing is slightly artificial, so you do not think of it too much in terms of can one function execute while the other one is going on, or can one instruction execute while the other one is going on. The assumption is that you have hardware which enables that, and under those conditions what can you do with it? Okay. So if I said, for example, that after A1, A2 can start, and in the next clock cycle, which is also idle, A3 can start. Next clock cycle, A4 could start or B1 can start. Okay. So what I am going to do is I am going to start B1, right, then B2 and B3, then I will have C1, C2 and C3. Unfortunately that is it, I can't run C4. Okay. I could run A4, but that complicates matters a little bit, right. I am not really interested in going down that line. So what I will do is I will instead keep this idle for the next 9 cycles, and then say from here onwards I can run D1, D2, D3, E1, E2, E3, F1, F2, F3, and from this point onwards, this is the end, I can start A4, A5, A6, etc. So this now becomes the block schedule, right. It has a latency, again the same 27 cycles, but the II is now interesting. The average is the only thing that you can really meaningfully talk about, okay. It is 27 by 3. So every 9 cycles I can essentially initiate a new call to that set of functions A to F, okay. So the question is this the best that can be done? Effectively, if you think about it, this is sort of like unrolling, right. What I have done over here is I have written out A1, A2, A3, B1, B2, B3, C1, C2, C3, and then the processor can straight away say, okay, A1, next clock cycle I can immediately start A2 because it has no other dependencies, then A3, then B1, B2, B3 and so on. So the unrolling will give you this and will allow you to bring down your initiation interval from 27 down to an average of 9, okay. The question is, can we do better? Okay. So what we are going to do tomorrow is to look at how we can rewrite this code in such a way that these dependencies could be shifted around a little bit and give us an initiation interval of 6, okay, which in this case is the best possible because you have 6 steps that are there inside the for loop. So you can't really look for an initiation interval less than 6, right. The same concept can then be applied to entire function level in hardware, and we will take that and we will look at that in the context of the FFT code and see how that can be used to bring down the latency.